Hello. This is George shoving his nose in my phone and saying hello to you. I just want to take a look at some other examples that really the process works the same, so I'm not going to focus on kind of the end of the process, but where the start is a little bit different. So, for example 4, notice here they want a particular solution, which means they gave me an initial condition to find a particular value of c. They are telling me they want me to solve it for y. They are telling me they want to make sure that I have a function of x. There's no plus or minus there. And then what's a little bit different about this, again, is really just the beginning part. This looks worse than the others, yeah? Dy dx equals some junk, and that addition always makes me a little bit nervous for these. So moving things to the left and the right with addition and subtraction isn't always a terrible idea, but typically is not a great idea. So what I have, I'm going to leave the left side alone for right now. On the right-hand side, that addition is an issue. So what I'm going to do over there is just factor it to turn that addition problem into a multiplication problem. So I have y times x plus 2. The fact that I am now multiplying two things kind of solves all of my issues. I can multiply both sides by dx, as we usually do. So the dx is fine now. The x plus 2 can stay where it is. And then I can divide both sides by y, or I'll say I'm multiplying both sides by 1 over y. It means the same thing. And we have this. So like I said, for this problem, really the only thing that's different from what we saw in the others is that we needed to factor before we started moving stuff around. If you tried some other algebraic stuff, you weren't going to get to this nice x times dx and then y stuff times dy that we have here. So from this point, everything works basically the same. You're going to integrate both sides. So as we did for the others, just go through and pause me, try to finish it up on your paper, and then unpause me. Hello, welcome back. So after the integration, we got a natural log showing up. I went ahead and used my initial condition at that point to find my particular value of c. What we then had, let me actually erase what I did in this step. I had natural log absolute value of y equals some other stuff. In order to get rid of a natural log, this is something we've talked about multiple times this year, just an algebraic skill, but getting rid of a natural log means throwing it on a base of e. Those are inverse operations, they undo each other. So doing that gets me to this point. But then I have the absolute values causing trouble. So I'm going to do just kind of down here. Forget about this problem for a second. If I told you the absolute value of w was 4, there are two solutions to that equation. Take a moment and think about what they are. If the absolute value of a number is 4, then that means that number was either 4 or negative 4, right? When I took the absolute value, it became positive. So you haven't probably done this a whole lot, but if I'm trying to get rid of absolute values, all I need to do is say that the other side might be positive or negative in order to give me that result. Similarly, something you have done before, if I say that y squared equals stuff, this is all very official, then when I take the square root on both sides, we do a plus or minus square root of that stuff. So, like I said, something you probably haven't done much before, but hopefully it makes sense, that getting rid of absolute values just means maybe you have a positive or a negative of what was there. So back to our problem, that's precisely what I did. I had absolute values around the y, so I got rid of those and threw a plus or minus on the other side. And then we have the same issue that we saw earlier. We've solved it for y, but the plus or minus means that we don't have a function. One x value gives me two different y values, a positive and a negative. So as we did before, I just have to pick one. The initial condition, 2, 1, tells me to pick the positive side. And now I've solved it for y, and I am left with a function. Moving forward, example 5 looks insane. Let's look at it one piece at a time. Particular solution means I have an initial condition. I'll find a specific value of c. They want me to solve it for y. They want to make sure I have a function, no plus or minus. And then I've also included just some restrictions on x and y, really just to deal with the absolute value stuff. The differential equation itself looks a little bonkers. What we would much rather have is dy dx equals some stuff, and then we can start moving things around. Here, I don't see a dy dx at all, but I basically do, right? A y prime. But I see it in 2 spots. No big deal. I'm going to factor it out wherever I can. And while I'm at it, I'm just going to move this other stuff to the other side. Again, kind of big picture goal is to get the dy dx, or the y prime, by itself. So if I rewrite y prime as a dy dx, and I divide both sides by 2x plus 9, then I'm in a form that I like a little bit better. It's still not separated, but it looks more like the other problems, which means it is time for you to pause the video and see what you can do to solve this differential equation. We had to do a little bit of different algebra to get to that point, but now it works the same as the others. So pause me, try it, and then unpause me. Okay. So where we ended just a moment ago, I had what was here in black. I took the integral of both sides, which involves some mental use substitution because of that 2x plus 9. Natural log showed up on both sides. My initial condition helped me find a particular value of c. And then we did what we did in the previous problem. We got rid of a natural log by using an e, and I got rid of these absolute values in my head by doing a plus or minus, but since the given y was positive, that's why I chose the positive version. And this answer is hideous, but fine for now. Because for multiple choice, that is not at all what the answer is going to look like. So here, just an algebraic thing. This is no longer a calculus problem, but I've seen enough confusion and issues and stuff with e's and natural logs, because it's been a while since you've done them, that I wanted to go through this process. Okay. Because what I have is a base of e, and then a crazy looking exponent that has natural logs in a couple different places. So what we can do is, using some properties of logs, we can rewrite the exponent to make that look a little bit nicer and then cancel some stuff out. But again, let's think about a goal. If I can get e to the natural log of stuff, e's and natural logs undo each other, and they would both disappear. The trouble is, this is not written as e to the natural log of stuff. It's just my exponent happens to have natural logs in it. So let's just focus on the exponent. Then we'll worry about what the e does to it and all of that. Yikes. But just with the exponent, my surface has had enough of me today. There we go. just in the exponent, I see a negative 1/2 natural log absolute value 2x plus 9 plus 1/2 natural log of 9. Just for some simplicity, I'm just going to rewrite that with the positive thing coming first. Because at this point, this is a property of logs. I'm subtracting two different logs. But before I can deal with that, I want to deal with these 1/2s. So I'm just going to factor out a 1/2. Natural log of 9 minus natural log absolute value 2x plus 9. So just factoring out the 1/2. And now things look a little better. I'm subtracting two natural logs with nothing messing that up. So thinking back to your properties of logs, this is a big one. Subtracting two separate logs is the same as dividing in a single log. So this is really natural log of quantity 9 divided by absolute value 2x plus 9. I don't really need those other parentheses, makes it look messy. And the 1/2 is just in front because I factored it out in order for me to combine those two natural logs. But this still isn't quite what I want because I just want natural log of stuff. So now I kind of hate that the 1/2 is in front, but that's a different property of logs. It allows me to take that 1/2 that's in front and throw it in as an exponent inside. This is the same as natural log of 9 over absolute value 2x plus 9 with an exponent of 1/2. The absolute values here, I keep writing them. There's nothing wrong with that. Officially, I don't need them. When we get to the end, I'll talk about why I don't really need them, but they're fine. What we've done just algebraically, in blue, we did the subtracting two natural logs trick. That's the same as dividing in one natural log, so that's what happened with what I've highlighted in blue. And then in red, a different property of logs tells me that a coefficient in front can become an exponent inside. But all of that was just to deal with the exponent in the answer we found a minute ago. And that exponent was thrown on a base of e. But by rewriting that exponent, now when we throw it on a base of e, now it is exactly what we want. It's a base of e, natural log of some stuff. Now I can cancel those. And by using properties of logs, and then the e and the natural log canceling each other out, we have what we want. This answer is fine. As I said earlier, the absolute values aren't really necessary because of what the problem said. The problem told me that my x's are positive or non-negative already. So when I multiply by 2 and then I add 9, it's still positive. So I actually don't need those absolute values in the denominator. They're fine, but I don't need them. Another thing I can do, instead of an exponent of 1/2, I can throw that all underneath a square root. That's fine as well. Or I could split up the square root. Square root of 9, principal square root of 9 is 3, and then square root 2x plus 9. That's fine as well. Here again, absolute values not needed, not required, but they're okay. Because they told me already that x wasn't negative, so 2x plus 9 is definitely not negative. The absolute values don't do anything. Okay. And then the last example is, again, just written a little bit differently, where instead of having derivatives being, obviously, I hope y prime or a dy dx, this time I've split that apart already. into two differentials. dx is a differential. It's part of a derivative, but it's not a derivative itself. dy is a different differential. It's part of a derivative, but it's not a derivative on its own. So here, I could, and in fact I will, kind of treat this the same way I did the previous. If you do these enough, you might notice how you could potentially skip this step, but it certainly doesn't hurt. That I'm going to reorganize this to get essentially just a y prime. So let's see. Subtracting normally makes me nervous, but here there's kind of no better option. So I have y squared plus 4, all of that times dx equals negative dy. This next step is really unnecessary, but if I'm using this up here as a goal, then it kind of makes sense to do it. I'm going to divide both sides by dx, and while I'm at it, I'll multiply both sides by -1. Change colors there. Change colors there. Come on, OneNote. I believe in you. So times -1. I did not have to do all of what I just did because when I start separating my variables, my first step is that I'm going to multiply both sides by dx. I'm going to kind of undo what I just did. But once again, if you want just a good rule of thumb for these, setting this as a goal, dy dx is by itself, everything else is on the other side, it doesn't hurt to do that because now it looks like what we've done, 5 of at this point. So here again, hit pause, try to finish that problem up, and then unpause. So after separating variables, I hadn't even actually done that part. After separating variables, you get what I have here in black. Integrating both sides, I'm going to get what I have in red, hopefully. Remembering this integral from an earlier unit, so from your, I guess, orange sheet at this point. They did tell me to solve it for y. They did tell me to make sure that I had a function. So everything else just becomes algebraic. And some stuff got moved around on my page, so bear with me. Really the only kind of strange thing that happens that we haven't seen before today, I guess, is that getting rid of arctangent on the right-hand side means introducing tangent on the left-hand side. That should be old news, but tangent and arctangent undo each other in the same way that e's and natural logs undo each other, or multiplication and division undo each other. Something else I've done here, you'll notice I kind of adjusted c as we went by saying it was 2c after I doubled, or I guess -2c even more specifically. And so in the end, you can say that there's a 2c showing up, or you might have changed the letter to a d, or I don't necessarily recommend this, but you can get away with it. You can just keep using the letter c throughout. I would advise you to use one of the first two options. The last one, there's some mathematical issues with it, but you can get away with it. But it can get confusing if you're using a c to represent the ending constant, because that's going to be different from the c you had at the beginning. Okay? And so as we did with the other topic for set A, I have just a little 2-question multiple choice thing so you can kind of see how you're doing, and you have an opportunity to tell me stuff you're confused about. Of course, feel free to email me with questions and work on the homework. It comes out of the textbook, and so since I figured you might not have your textbook at home, I have just taken a really lousy picture of the textbook and circled the problems you need to do with some instructions here. You can do it in OneNote, which is preferable, but if you hate OneNote as much as I do, you can also do hard copy. So that does it for set A. So I'm going to post this stuff online and send it out to you through OneNote. Set B will be posted next Monday by noon. Bye, guys.